fine. Yeah, tell me 1 plus 0 plus 0. What is the value? 1. And here 1. I have you understand 1 plus 0, what is the value? 1. 1 plus 0 again 1. 1 plus 0 again 1. If I perform, my addition is 1. 1. Okay, here 1 plus 1, what is the value? 1 plus 1. Student? 1 plus 1, what is the answer?
0, 1.
0, 1. My carry will be 1. Again 1 plus 1. 0, 1. 1 plus 1, 0, 1. Okay, 1 plus 1, 1, 0. 1, 0 plus 1, 1, 1. So 1, 1. 1 plus 1, 1, 0. So 0 will be there, again carry. Again you tell me 1 plus 1, what is the value? 1, 0. 1, 0 plus 1, 1, 1. 1, 1 plus 1, what is the value? Tell me. 1 plus 1 again 0. Again 1 plus 1, 1, 0, 0. Is it correct or not?
Correct.
Yeah. So now 0 will be there. Now what is my carry? What is my carry? This is my
1, 0.
This is my carry. Okay, you see?
Ma'am, what to do with the carry, ma'am?
Yeah, this is my carry. Okay, but you all know what is the procedure. If the carry is there, again I have to add with this sum. So 1 plus 0, 1. Again 1 plus 1, 0, 1. So this is my checksum. Have you seen? This is my checksum. I got this checksum. I got this checksum. Checksum is verified. It is correct. Thank you, Soumya Deep. Okay. So have you seen? This is my checksum value. Okay. This is sender side get over. Checksum is created. Okay. Now, once the checksum is created.
Ma'am, you didn't say what to do with the carry, ma'am. Should we discard it or?
No. You should not discard. What is the procedure they told? They ask you to add the carry with the checksum.
Okay.
Previous case, we don't have a carry. That's why we kept this as a checksum. But now we all know now we perform the addition. Now we are getting 3 bits. Actually, it contains only 8 bits. Okay, 1, 2, 3, 4, 5, 6, 7, 8. If it exceeds 8 bit, that is your carry. You all know that. So that carry is added here.
Okay, ma'am.
Okay. Now, this is my checksum. But what is the next procedure? Can anyone remember?
Complement it, ma'am. Complement it.
Yeah, very good. One's complement. So what is the one's complement of this? I have to take the one's complement. What is the one's complement? 1, 1, 0, 1, 1, 0, 1, 0. That is only added here. That is only added here. Are you clear?
Yes, ma'am.
Yeah. After this is all that they are saying. Now we have to go on which side, ma? Receiver side. Okay. So receiver side, you just see this is my checksum value. Now I am performing all the additions. See, I am performing all this addition. So here again, what is my carry? What is my carry? 1, 0. So I have to add that 1, 0. You just see all my bits are 1. Then automatically the checksum received is correct. And I have to accept the data. Is clear? Just only the
Clear.
checksum.
Clear, ma'am.
Yeah. So have you understand the checksum concept? So checksum, the sender side, they perform all the checksum. They do the ones complement and then they will send us a packet. Again, here it will perform all the checks thing. And some of the result, if the sum is 1, they will keep, or sometimes they will take the complement and they will check whether all the results are 0. They will keep, otherwise discard. But both the concepts are same only. Okay. If all my sum is 1, then if I take my complement, definitely it will be all zeros. So both the concepts are same. So they are saying that this is at the sender side and this is at the receiver side. Is clear? So we have completed the error detection methods. We have completed the error detection methods. Yeah, have you understand this?
Ma'am, can you go to the previous slide once more?
This slide,
Ma'am, the last answer of that question, ma'am, the receiver's solution for that question.
Oh, that one. This one.
Yes, ma'am, this one.
Okay.
So at receiver's end also, do we need to add this carry, ma'am?
Yeah, definitely. That
Okay,
is they
ma'am.
told you. If the carry
Okay,
is
ma'am.
generated, you have to add. If it is 8 bits, beyond the 8 bits you are getting. For example, that particular block contains 4 bits now. If it beyond the 4 bit, that will be the carry. Okay. That is depends upon the number of bits in each block.
Got it, ma'am.
Okay, so error detection method is one thing, and here we will see with both error correction as well as we used to say coding. Okay, so we are saying now the redundancy bit and all. So block coding, convolution coding, or linear coding. We used to say we will see about the block coding first. So give the heading block coding. Okay, block coding. This is my data words. Okay.
And why we use coding, ma'am?
Coding. Sometime why we are telling now, we are sending the redundancy bit with the data bit now. The technical word how they will say now. In the sender side they will say data word. In the receiver side they will say code words. How it will happen now? See, just assume this is my sender side. Okay, this is my sender side and this is my receiver side. Okay, my data word will be there. Okay, and there is some algorithm is there. Then using that algorithm, we will add the redundancy bit. So the data word will become code word. And that code word will be transmitted in the unreliable transmission. Because why we say unreliable now? We can't be sure that the received word will be correct or not. Okay, and once again the receiver side, I will receive the code word here. Again, there is an algorithm to check whether the code word is correct or not. Then we will receive the data word. Is clear? So can we understand what is data word and what is code word? Sender side, yeah. So now you understand here very clearly. I have a k bits. So 2 power k data words, each of k bits. That is, for example, I told you this is 8 bits, this is 8 bits, this is 8 bits. Now they are saying 2 power 8 data words will be there. Okay. Now we will say there will be n bit in the code word. What is n bit in the code word? Now we will see that 8 bit is the data word. We will add R stands for what? R stands for what? Yeah, redundancy bit. So n equal to k plus r. That sometime when we are seeing the redundancy bit. Okay, while we are seeing sometime when we add 3 bit, my CRC value will be also 3. If in the cycle redundancy check, sometime in the vertical redundancy check, there is only 1 bit will be the redundancy bit. And here while we perform the checksum, we have a 8 bit redundancy. So that's all depends on the method. Okay, so you all understand. I'm saying my code word is generating now. The code word length is equal to data word, k bits of data word plus redundancy bit. Is clear? So n bit equal to what? N equal to k plus r. Okay. Now, one simple example you have to understand. Okay, they are saying 4-bit, 5-bit block coding. The way they will give the like this. What is 4-bit? What is 5-bit now? This 4-bit they will send for data word. Okay, this 5-bit they send mentioning for code word. I told you how the code word is created from the data word. So, for example, how many data words now? 2 power k. That we mention as a data word. 2 power 4. But when you are saying the redundancy bit now, okay, n equal to what? K plus r. So what is my n value they are saying now? What is my n value they are saying now? What is my n value now here? In this case, what is my n value? N value, yeah, 5. So 4 will be your data word and 1 will be your redundancy bit, that n equal to 5. So when I perform 2 power n is nothing but 2 power 5 is nothing but 32 code words are used. But how many data words are there? How many data words? How many data words are there?
2 to power
2 power 4. 16 data words are there. But how many code words are generated? How many code words are generated?
32, ma'am.
32. Just you see, the remaining 16 are unused. They don't have any other purpose, because we want to secure in a packet whether we have to check whether my received bit is correct or not. That's why we are adding the redundancy bit. Only 16 data words are there. Remaining 16, that is 32 code words are there. In that 32 code words, we are saying that 16 only data word. The remaining 16 are be unused. Have you understand? This is the best way they will explain the 4-bit / 5-bit block coding. Are you clear, ma? How the value of R came? R. Now only we were seeing, na Soumyadeep, we were seeing that all cases we are adding. R is redundancy bit. Okay, this is the logic. Data word, code word. Okay, there is algorithms to generate the redundancy bit. That's why I told you in vertical redundancy check, there is only a single bit. Okay, but when you do the checksum, the redundancy is 8 bits. When I perform the CRC, that depends on the key it will generate. Okay, so that for example, K is the data word length and R is the redundancy bit length. The code word length N equal to K plus R. Have you understand? K plus R. Okay, thank you. Okay, that is I have told you. K bit is the using generator. We are generating R. That is my redundancy bit. N is equal to what? Always don't remember, forget this formula. K plus R. Here again the code bit will be there. Checker will do all the kind of checking. Okay, so while we see in the error detection method, parallelly we are doing the correction also. CRC also we performed all VRC, LRC, cycle, CRC and checksum, all that we are doing error detection as well as error correction. So don't say that, ma'am, you didn't tell about the error correction. Sender side error will be, the code will be sent, and receiver side it finding the error as well as it is correcting the error. Okay, sometimes it will reject. That is mainly depends on the algorithm, checker algorithm. Okay. Okay, now I will tell you this. This is one thing. Okay, how many redundancy bit is added here, ma? What is my K value?
1, ma'am.
Very good. N is 3 now. My redundancy bit is 1. Okay. Actually, some cases they will do. They are performing the parity bit. Okay, this is your redundancy bit. Okay, sometimes they will tell you, no, it is performing the XOR operation, whatever may be. Now you tell me according to parity bit, odd parity, sorry, even parity. So here, what will be your redundancy bit? 0. Here, how many number of ones are there? We all know
Odd number, ma'am.
Odd number of ones are there, your parity bit will be 1. Even number of ones is there, your parity bit will be 0. That is the concept we are seeing. So 0, 1, here my redundancy bit is 1. Because only 1, 1 is there. Here again, only 1, 1. So my redundancy bit is 1. And here 1, 1. Again, when I see here 2 even number of 1 inside. So my parity bit is 0. So this is the way they are correlating the data word and code word. Okay. The same thing they are saying. Okay. What they are giving the best example now. 0, 1 they were giving 0, 1 they are giving 0, 1, 1. Instead of 0, 1, 1 I am getting 0, 1, 0 now. Whether it is correct or not. Whether it is correct or not. My data word is 0, 1, ma. My code word is 0, 1, 0. It is correct or not?
Correct, ma'am.
How come? We are using even parity algorithm. Na? My data word is 0, 1. Now, how come 0, 1, 0 is correct? 0, 1, 0 is? How many number of 1 should be in our code word, Sagar? How many number of 1?
For even parity, there should be even number of 1. For odd parity, there should be odd number.
Yeah, that is the checker side. They are saying that's why this is the blocking. I have to do that 0, 1 na. My code word should be 0, 1, 1. You understand here? 0, 0, 0. Okay. 0, 1, 1. 1, 0, 1. 1, 1, 0. So you just see this is my parity bit, and this is my that is a redundancy bit, and this is my data word. So what it will do, the checker na, it will discard this redundancy bit and they will get the data word. You just see 0 0 here, 0 0 here, 0 1 here, 0 1 here, 1 0 here, 1 0 here, 1 1 here, 1 1 here. So that means it will be accepted. Now I am saying 0 1 is my data word. Now I am saying 0 1 0 is code word. That is correct or wrong? That is correct or wrong?
Wrong, ma'am.
Wrong, because we all know that it's a even parity, even number of one. So it will discard this code word. Or else one more problem is that I can able to find out it's because one bit error one thing. We all know type of error. We have seen that single bit error, multiple bit error, and one more bit error is what? Single bit, multiple bit, and one more bit error is what? One more bit error.
Burst error.
Very good, burst error. Okay, so here we can clarify this. This will be for one bit error. We can understand that, okay, definitely the problem in the code word, it will change it. Okay, this is they have explained. Same thing, error correction. Okay, so sometime it will correct the error. That's they are saying. Always it not will be discarded. Sometimes the error will be corrected. K bits, redundancy bit is generated, and n bit is nothing but k plus r, and the k plus r will be transmitted in the code word, and again here the r will be left, and only the k bits will be your receiver data word. It should be always correct. Okay, now in this case my data word is 0 0, and I am generating the code word. I'm generating. Okay, so when you see that, well, how many redundancy bit is added in this case? How many redundancy bit is added? Yeah, redundancy bit is 3, and n is 5, and k is 2. So n equal to k plus r. Any some algorithm they perform. They perform the algorithm and they will get the value. Okay, so they will say that using some XOR concept, or using some CRC, or using, that is the way. Another example I gave you to understand the purpose. Okay, not always the redundancy will be 1. Redundancy can be 1 or 2 or 3 depending on the value. Okay, so now here they are saying that whether I'm saying this is my data word and this is my code word, whether I am getting my code word is correct or not. So how they will do the checking algorithm? They will do the XOR with the previous one. I told you already this concept, modulo 2 arithmetic. If my both the bit are same only, I can say what will be my XOR concept. What will be my XOR value?
For same, it's 0. For different.
Yeah. So this is 0 1 0 1 1. This will again perform with that value. If I get XOR now 1 1 0 1 1 0 0 0 0. So if all are 0, then I can say that my code word received is correct. My code word received is correct. So they will perform with 0, and once again they perform that. Even though there is one bit is get changed, then if I perform my XOR operation, automatically what happen now, it will compute the value as a error, and it will be always used to detect the single bit error. That's all to understand that. It's not doing the burst error. It is detecting only the single bit error. Okay. So XOR you all understand. If both the bit are same only, I will get my 0. Or obviously, if there is a difference in bit, then I can understand that it is a 1 bit error. If 2 1, if I'm getting here all are same. If I'm getting 0 1 0 0 0 means I can say it is a 1 bit error. If I'm saying 0 1 1 0 0, na, it is 2 bit error. If I'm saying 0 1 1 1 0, na, it's a 3 bit error. If I'm saying 0 1 1 1 1, na, it is 4 bit error. But this particular blocking coding now, we are saying it is used to detect the single bit error. Okay, I think the same thing only they were saying that. Okay, if both this bit are different now, they are saying that it is a single bit error, and it can able to detect the error, then automatically it will correct it. Okay. And another important topic while we are going for now block coding, convolution coding, or linear coding, we will use Hamming. I think we heard this word before in digital, Hamming code. Yes or no? Yes or no, ma?
We don't know about Hamming code.
Yeah, you hear. Okay, now we are going to find out the Hamming distance. Okay, we are going to use the linear coding concept, and we are going to use the Hamming distance. Okay, now how they will perform now? We all know 0, 0, 0, 0, 0, 1, 1. Okay, now if I have to perform the XOR operation, this is all you know, this is nothing but your XOR operation. If I perform the XOR 0, 1, what is the value? 1. 0, 1, 1. 0, 0, 0. So how many ones are not? 2 ones are there. So here we will say the Hamming distance is 2. Okay. Now again I am performing the XOR for with 2. I am getting my resultant value here. How many ones are there? How many ones are there? How many ones are there, ma?
3.
So my Hamming distance is
3.
3. Here my Hamming distance is 2, and here my Hamming distance is 3. Have you understand?
Ma'am, can we say that Hamming distance is the XOR result of 2?
XOR result, and it will count the number of ones in the result. You know,
okay,
we apply the XOR operation on the 2 words and count the number of ones in the result is your Hamming distance. Okay. Now you just see, this is the data word and this is the code word. Okay. Now they are finding the Hamming distance for each and every bit, each and every code word. This is another way, linear blocking. There they are doing. Now you see, they perform the Hamming distance of this 2. Then they perform the Hamming distance of this 2. Then they perform the Hamming distance of this 2. Then they perform the Hamming distance of this 2. Then they perform the Hamming distance of this 2. And they perform that. So all possible way they will find out the Hamming distance. You see, so how many, what is the Hamming distance value you are getting in all the cases? In all the cases, what is the Hamming distance you are getting, ma? What is the value you are getting in all the cases? 2. So they will take the d-min. D-min means minimum Hamming distance. That value is 2. The minimum Hamming distance is 2. Sometimes if your Hamming distance is 2 and you are getting 3, what will be your minimum Hamming distance? You are getting 2 as well as 3. So what will be your minimum Hamming distance? The minimum Hamming distance is the
average, ma'am.
Not average. It's the smallest Hamming distance between all possible pairs in a set of words. Okay, if you are one set you are getting Hamming distance as a 2 and another set you are getting Hamming distance as a 3, now the minimum Hamming distance is the smallest Hamming distance. You take the next example, this example. Okay, this example, again the same thing. It will do perform with this, and again it will perform with this, again it will perform with this, and all possible way it will perform. While performing, in some cases, what is my Hamming distance value? 3. In some, what is my Hamming distance value? Hamming distance na the total number of ones in the word while I perform the XOR operation. So, for example, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1. So now tell me 1, 1, 0, 1, 0. So what is the Hamming distance for this case? How many ones are there?
3.
2. 3. How many? Yeah, I think Pujita have understood. If your Hamming distance is 3 and 4, the minimum Hamming distance is 3. Have you understand this? Any? Yeah. In this case, we are getting how many ones, ma? 4 ones in your answer. So here you take down this formula. D minimum equal to S plus 1. What is the D minimum for this case? For this case, what is D minimum? What is the 3? So tell me what is the value of S? What is the value of S? What is the formula for D minimum? Yeah, very good, Soumyadeep. S equal to 2. D minimum equal to S plus 1. S value will be 2. Kindly take down the formula. This is from your...
What is S?
S is that saying that S will be up to S error it will detect. Okay. For example, D minimum is 3. So what is my S? According to this formula, what is my S? So it will detect up to 2 errors. Up to 2 bit of error it will detect. Have you understand? Yeah, have you understand or not? We will go with some examples also. Don't get confused.
Yes, ma'am.
Okay. I think if possible, what I will do, I will put this today's video as well as last class video in your group. Okay. I will convert and put. If you can't understand, you may recall it and you may check it. It's clear? Okay. So now this is the geometry concept for detecting error detecting. So they told you na D minimum equal to S plus 1. Okay, S will be up to how many error it will detect now? 0 to S error. We all know definitely D minimum equal to S plus 1, which is greater always. D minimum is always greater than S. Always greater than S. So you have to understand this is for finding the error detection it will find out. Okay, the next case. Next case is error correction. Did you take down the formula? D minimum equal to what, ma? S plus 1. The next one is nothing but error correction. What is the formula now? D minimum equal to 2t plus 1. Okay, guarantee of correction up to t errors. Okay, we will see with one example. D minimum, the next formula is 2t plus 1. So definitely my D minimum should be always greater than this 2t. Okay, so error correction, this is on a error finding. It can do S errors. And here error correction, any corrupted code word. Okay, I can able to detect up to 1 to t errors. Okay, so t is nothing but a error. Now you people kindly take down this case. D minimum, what is the value, ma? What is the D minimum value? What is D minimum value? Tell me formula. What is D minimum formula, ma?
D minimum is S plus
1. Okay. So what is my S value? What is my S value? What is my S value? 3. And you know in error correction, detection and error correction. So it can able to detect how many bit up to. It have a guarantee to detect how many bit, ma?
3 bits, ma'am.
3 bits. Very good.
Ma'am, 3 bits of consecutive error or 3 bit of
3 bit error it will do.
Errors.
Okay. Not consecutive. 3 bits it will do. Okay. Now D minimum equal to one more. Error correction. This is for detection. Is clear? This is for detection. And this is for correction. Correction D minimum equal to we all know 2t plus 1. 2t plus 1. So tell me what is my D minimum value?
4.
4 equal to, and we all know that 2t plus 1. Okay. And one more condition we have written that D minimum should be always greater than the 2t. Am I correct or not? So my D minimum value is 4 now. How many error it will correct? What will be my T value?
1.5.
1.5, it's not possible. So we will round off to 1. Why? Because now you just see here, it should be great. Now we will say it can, how many it will direct now? Only one error. Sorry. Am I correct or not? It can correct up to one error. 2 into 1. If I keep a t equal to 2, that's not possible. So 2 into 1. So it can able to detect 3 errors, but it can able to correct only how many errors? Only one error. Yeah. No, don't say that. There is not possibility of 1.5 bits is there. 1 bit is there. Is clear? Yes. Have you having any doubt on this case? Have you having any doubt on this? Sagar, have you understand that?
Yes.
We have a guarantee to detect 3 errors because S value is 3. But correction, it cannot able to correct because my t value is 1. So error detection is S plus 1 now. Error correction is d minimum should be greater than 2t now. It can correct up to 1 error. That is the capability of this Hamming distance. Hamming distance, we can able to find out the Hamming distance, how many bits it can able to detect the error and how many bit it can able to correct the error. So what they are saying now, that d minimum will be always 357. Okay, now you take one cases for me. Okay, now consider d minimum equal to 5. In this case, kindly tell me, ma. D minimum equal to 5.
It will be 4, ma'am.
Yeah, tell me how many bit it will detect the error.
4, ma'am. 4 bits.
Yeah, very good, very good. 4 bits it will detect the error. So D minimum is 4. Sorry, I gave you 5. 5. So it can detect up to how many error? Detection means we all know S plus 1. So it will detect up to 4 bits. Okay. Now we all know D min correction of error. What is the formula? D min should always greater than 2t. What is my D minimum value? 5. So how many bit it can able to correct?
2 bits, ma'am.
Yeah, that is very simple. It can able to correct up to 2 bits. That's why they are saying that, concluding that your error correction or your Hamming distance should be in the odd minimum distance. Odd minimum distance. Yeah, Pujita correct. Soumya Deep correct. Odd minimum distance. It should be 3, 5, 7. This way is that it is easy. So that we have to generate our code words in the way. Okay.
Ma'am, can we also conclude that S will always be greater than T?
I can't understand. Huh?
Ma'am, can we also conclude that S will be always greater than T?
Yeah, S will be, we cannot conclude that. S is always greater than T. In some cases, it will be differ. Okay. But when you see to that, always it is detecting 3 error now, it is correcting up to 1 error. I think that relationship they didn't tell, but you all see to that. I think your statement is correct. D minimum is greater than S. Am I correct or not? And D minimum is greater than 2t. So if I correlate this, definitely I cannot able to come to the judgment that if I am replacing this S by 2t, now 2t greater than S, or also sometime I can say. It's clear, ma? So I think
Yes,
that thing, maybe I will check out that S and 2t will be correct or not. But while we are seeing all the cases, what you said, that statement is correct. Okay. Now linear block codes. Okay. I told you same thing. Linear block codes. What they are saying now? Performing the XOR between these 2 bits. Okay. What is 0, 0, ma? What is the XOR operation of 0, 0?
0, ma'am.
0. Yeah. XOR operation of 0, 1?
1.
1. XOR operation of 1, 0?
Again 1, ma'am.
1. XOR operation of 1, 1?
0.
0. Okay. So here they are saying that this is using some modulo 2 arithmetic, they will create the code word. Okay. And this is one of the method they were saying. And this is also creating 4 keywords. You all know that here we are having only 2 data word and 3 redundancy bit. The same way they will perform the XOR operation and they will get it. And here you just see how it is performed for this bit. I will tell you how many data words are there. A0, A1, A2, A3. You consider A0, A1, A2, A3. Okay. Now the redundancy, how many redundancy bit is added in the code word? How many redundancy bit is? Only 1. So how they are saying now? Redundancy equal to A3 plus A2 plus A1 plus A0. This is the way they will generate. For example, you take this example. Okay. 1 plus 0, what is the answer? 1 plus 0?
0, 1, 1.
1. Again 1, 0?
1, ma'am.
1. 1, 1?
1, 0.
No addition.
0, 1, ma'am.
0 only. Yeah, XORing operation. Have you done 1 plus 0 plus 0 plus 1? It is not a plus. It is a XOR operation. 1 plus 0, what you will get it? 1. Again 1 plus 0, what you will get it? 1. Again 1 plus 1, what you will get it? 0. So this is the way. For example, 4-bit data word is there. I want to get the 5-bit data word, or else we again it will be similar to your odd and even parity. If I want to get the even number of ones in my code word, I have to check. I have to add whether odd number of ones. I have to add my parity bit as a 1, and if even number of 1 is there, then my parity bit is 0. So this is they were saying that in the linear block coding, they are performing with the XOR operation and they are getting the code word from the data word. Okay, see, this is the way. This is my data word. You all know R0 is my parity bit now. They are performing the XOR operation A3, A2, A2, A1, A1, A0. So I will get one parity bit. That is my code word. And finally, in the checker side, it will check that parity bit whether this bit is correct or not. If it is that, it will accept or else it will discard. I think till this 12, 11, till the next one is nothing but Ethernet. I think Ethernet within 4 minutes. I can't
5 minutes only left, ma'am.
Please share this PPT. Yeah, definitely. What I have taught. What is the slide number? This is till this slide. I will share to you people. Till this slide number. Ethernet is nothing but I think we have completed all till this topic.